before I start, anything that you wanted to ask but didn't fit in the time to ask, or anything you want to learn that I didn't put yet on my board to memorize? Well, I already told all these specific things like align as and memory model. So anything you deliberately want to, or you'd like to know that I didn't tell you so far about, that came up during the break? Two things.
Well, something I would like to learn is about this restrict that exists in C11, and you don't have it in
Restrict doesn't exist in C++.
Yes, exactly. But this is, I mean, the compilers G++ and Intel support it anyway.
I have no idea what restrict means because it's not C++.
Okay, but
okay, restrict is a keyword to tell to a function that a pointer is not aliased with some other pointers. And all the accesses to through that pointer will be safe.
Well, a good compiler can do some alias analysis anyway.
But
not always.
Yeah, this is the problem, not always. So GNU Intel supports an attribute for that, but it's not in the standard, and I don't think it's ever been discussed at the moment.
No.
By the standard
not at all.
committee, which is a problem. I agree. I think so, at least.
Yeah, but there were two more hands, yeah.
Okay. Two? Oh, okay.
So I have one request. Like when you will be mentioning about algorithms and nice way to write the code, not only can you mention about is it nicer or more proper way, but also regarding the performance, if it's faster or the same or slower, because this is what I'm really interested. If the constructs, for example, iterating over arrays will be the same or slower?
They will be the same or faster. Because you might end up that the implementation of the algorithm libraries actually do specific optimizations for, let's say, random access iterators which are on arrays, or you might even be able to use parallel versions of the algorithms provided by libraries with the same structure as you get. And then in C++17 or later you might get, or I guess C++17 you will get standardized parallel versions of the algorithms to use.
I heard that this include guard is going to be replaced, and I'm wondering with what and how this will behave in the future.
Let's say include guards will stay around for some time. There are two competing proposals for a thing called modules, where you get rid of header files and have kind of module specifications that export things. And I'm not sure when and what we will get in the end. It's Microsoft versus the rest of the world. And Microsoft has implemented something nobody is happy with, but the others don't have an implementation. And that's currently the fight going on in the Senate's committee. And I don't want the Microsoft version, because it lacks backward compatibility with existing header files with macros and so on. And that's kind of Microsoft can do it on their own because they own the platform, but it's not very portable beyond. And Mauro might add if you have paid attention to the modules proposals. Not really.
Well, I paid a little attention. That my impression is that it's not clear what we will get, if we will get something.
Sorry to say no to some of the questions. Okay, let's go ahead. We found out about initialization. These are some examples of what you can do. You can default initialize. You can even have array initialization. You can use not only also, let's say, existing variables in an initializer list. It doesn't have to be literals only. You can initialize vector elements, and if you write a class, you can use curly braces here in the list of base classes and member variables. And that's a new feature of C++11. You can provide initial values for member variables. That way you don't have to specify the member variable in the constructor. It will always be initialized with that value unless you use a different initialization in a constructor. That's called non-static data member initializers, and these things used to be called non-static data member NSDMIs, and because nobody liked that name, it was just recently introduced in the standard as a default member initializer, the terminology to have these initializers. You could use equal in that case as well, but I prefer curly braces here. So we've seen that already. And in C++ 11 and 14 and with auto, just a reminder, this is a very silly example, but it shows you what you can actually get. I equals 3 int, that's clear. If I use an ampersand in front of a name, I introduce a reference. So J is actually an alias for I. It's exactly the same memory location, just two names for the same thing. You usually wouldn't do that unless J would be a parameter of a function where you pass in a reference, so you can modify the original place within the function as a side effect. If you use auto, you would take the value that's referred to on the right-hand side. So even though J is a reference to an int, the type of the expression, if you write J, is an int, because it will access the value on the right-hand side of the assignment, and that just gives you the value, which is 3, by the way. So K will be initialized with 3, and the type of K is int. If you want to keep that reference type, you have to use deckel type auto, and that will, if you write J, it will look into, okay, the definition of J is an int, oops, sorry. The definition of J is an int reference, so L will be a reference to int. It will be another alias referring to the same location as J, and that again will be I, the variable I. And now we get these ampersand things. And ampersand was introduced to have so-called R value references, which these two aren't, or not necessarily. If you use two ampersands in a context where there's type deduction, it is actually almost like the deckel type thing. It will keep references around, and it will introduce an R value reference if the right-hand side is, or if the type is actually an R value. So if you use two ampersands and auto with J, it will be, okay, I want a reference to what J is, and J is already a reference, so you stick around with reference. If I write I refer to the value stored in I, which is 3, an int. And there, the two reference symbols, you get actually an R value reference. So what is an R value and an R value reference? Just flip around. When you write A becomes B, on the left-hand side, A is an L value. Because on the left-hand side of the assignment, That's where you can assign to. An L value always denotes a place in memory, a variable, where you can store something, depending on the type of A. And B is called an R value because it's on the right-hand side of the assignment. That's just a value. And now in C++11, things became a little bit more complicated. That was more or less introduced at the time of C, or maybe even before, but at least C has these terms, L value and R value. Who has never heard of L value and R value? Now all of you have heard of that. Now in C++11, there was a desire to have a thing called move semantics and optimization of, let's say, passing a value to a function or returning it from a function without having a copy overhead if there's a large data structure, especially that if that's allocated on the heap. And now things got more interesting. There was introduced a thing called let's say how we I start with the root. We have values, and on one end we have R. Let's see if I can get the general L value, R value, and a pure and X value. So we have more value categories. We still have L values and R values. And there's a new thing called an expiring value. That is something that is there that you can steal from. Let's say it like that. Or take the guts out of, because you know it will no longer be used afterwards, though you just take it. Like the leftovers from the break. If there's a Gipfeli there, now somebody can go there and just steal it, and it's done. The thing is, to be an expiring value, it has to have a location where you can steal it from. So it's what's called a general L value. Generalized L value says, okay, there's something with a location in memory that you can refer to. And it's an expiring value, so it's also an R value. It's something you get on this side of the assignment, on the right-hand side of the assignment. And all of those are values. And now what's a pure R value? That's something that doesn't have a location. If you spell out the integer 42 in your program, that's a pure R value. It will not be, you cannot steal something from it. It doesn't have a memory location. It will go directly in a register or whatever, wherever the compiler puts it, but you don't have any access to where it's stored. So that's a pure R value. That's just what, let's say, a mathematician would call a value. It's there without having a location. These two have a location that you can either assign something to, and an expiring value you can take something from. Let's consider an example that's more interesting. If an L value is a vector and you assign to the vector, you replace its internal guts with the memory stored for the elements with a new memory with new elements. If you assign from a vector, you can actually, and that vector is no longer useful, you can take out the internal guts from the vector, the heap memory that's it's managing, and store it in some other vector. And that's what the expiring values are used for. To get such an expiring value, you would usually use std move around a variable. Is that still readable? Move does nothing except saying, okay, I will no longer use that variable afterwards. Oh, the only thing that is allowed with that variable afterwards is reassign a new value, or forget it, destroy it. Usually you don't have to care about all these things. If you just pass around values, the compiler will optimize anyway. If you no longer use that variable, it might just, and for example, return such a variable from a function. It will do return value optimization without copying, let's say, a huge vector around. But with standard move, you can guarantee that no copy will happen. And now now you can have references to L values, we can have references to expiring values, and we can have references to pure R values, or to any kind of values. These are, let's say, make the example with int, called int ref. That's L value references. To all the others, we can have const references. Goes for pure R values, for expiring values or L values, we can use const references. For expiring values, that's where the two ampersands come into play. They are called R value references. They can refer to an expiring value. And now I confuse everybody, and I hope you forgive me for that. So actually, if we use these two ampersands in a type-deduced context, we either get a reference or an R value reference, depending if the original that we pass in is already a reference or is just a value, then we get an R value reference. That's what these two ampersands with auto map either to a reference or to an R value reference. Now there's another thing in C++. I need more space. Let's say I write int const ref re equals 42. Is that valid C++? What happens here? I define a const reference to a temporary value. And that's fine in C++ because once I have a const reference to a temporary value, that value will remain valid unless this reference goes out of scope. That is a trick that allows us to parse 42 in a place where I have a reference const int parameter, for example. And it also works for local reference variables or local references that aren't variables that keep that value around. So if that would be a vector with values, I can have a vector const reference to that vector of values. That vector, even though it's just a literal there that I can specify now, would stay alive until that const reference goes away. The same thing works also with R value references. This R value reference, double ampersand int, is something you can take something away and it will keep that temporary alive until this reference is forgotten, until the block ends, wherever it ends. And again, if that would be a vector with, if we would construct here a vector with 1,000 or 1,000,000 elements, that vector would stay alive until that R value reference would go out of scope. The difference between these two is this you cannot change, but this you can steal the guts from. You can take whatever it is, and if you return it, it will guarantee to just return the guts without without copying. If you pass it, well, if you pass it a function, you have to use the move to actually pass the guts there to lose the inner features. Yeah.
Peter?
Question.
So,
Okay.
yeah, sorry. So in the second case, just double checking if I understood correctly. So in the second case, if I want to keep 43 alive outside of this scope, for example, by passing it to another function, I should pass it with move. Otherwise, it will not survive.
Well, no, let's say, if you pass this to another function,
Yes.
it will, because that's a name, it will depends on the signature of the other function. If that other function takes it by const reference, that's fine. If the other function takes it by R value reference, you have to use to move. If the other function takes it by value, it will just copy.
Okay.
But copy might be implemented as move depending on the type, but for int it will copy and move are the same. So that's, it's only, what I want to show here is that either reference or R value reference can be used to keep things alive for the scope, even though these are temporary objects.
Okay, thank you.
Just consider this is calling deep thought, not 42 literal. And the return value you get is there until you forget it again. We've seen that already. Okay, that's my driver's license for C++ that I give my students. If you write your own container class and want to use these initializer syntax, initializer list syntax to keep your elements or take elements into your system, you need to use the type standard initializer list. And that's a generic type, so you pass the values in. So it has to be homogeneous, initializer list, whatever, double T or int. And if this is my class, use vector member T, I can pass in this initializer list into a constructor. And because I cheated, I used just the vector as my member variable, I can pass on that initializer list into my vector to initialize the vector with. Otherwise, initializer list behaves like a container. It's not really a container. You cannot put something into it on yourself, but you can use begin and end iterators to get all the values within the initializer list and do something with them in your constructor, for example. So you could use the initializer list also as the right-hand side in a range for loop. You can just spell out also curly braces here to iterate over individual values given there. Come on. That's when you copy your slides. And there was a big question, going back here, on algorithms. And that's a big thing when, let's say, you learn programming. The first thing you learn is decisions, if statements. The second thing is loops. Some people first learn loops and then decisions because you can, let's say, write an if statement using a while. Some people learn recursion first, but that's rare. But most of the time, especially if you study computer science, you will get a hard time to learn all about algorithms and data structures. And as a practitioner programmer, that's the worst thing you should have. The first thing you should forget, because you're, except for very few, you're a very bad algorithm designer usually. So you better use the algorithms others have implemented already, because writing your own loops is very error prone. I confess I usually get 50% of my loop conditions wrong the first time. And so better I don't need to write the loop condition myself. And that's where actually C++ shines, because in contrast to many other languages, we have a library of a lot of algorithms where some of them are not quite that intuitive. are at least not that easy to spell out yourself, like next permutation, for example, which is a tough thing. But also for simple things like copying around values or searching values, there are algorithms already implemented for you. And the good thing is they work with almost all containers, especially also with arrays, for example. So you don't have to, let's say, rely on any kind of specific API to use these algorithms. They're just there for you to work with. And a few of you already know about them, but many of you haven't used many of these algorithms. So what I would say, whenever you see a loop in your code, even if it's a new range-based for loop, watch out. Caution. You need to write test cases for it, because the condition might be wrong. Loops tend to work with side effects which are somehow hard to argue about. And especially some of the loop conditions might be so slightly wrong that they are hard to recognize. Like a one-off error that don't give you any problems in your test cases, because maybe the data is just aligned that way that you always read a 0 and that doesn't change your value, for example. Or you start one late and your data isn't important enough in the position that you miss, or you step over twice, only every second element, or whatever you can do wrong with the loop condition. The standard library provides algorithms in more or less 3 headers where you have, or 2 headers, algorithm and numeric, and some infrastructure to use, better make use of the algorithms is in the header functional. Now, as an example, I do some examples that are not that useful for your code bases, but to give you an idea what's behind the algorithms, to show you before and after, with and without the algorithms. So like counting characters in input, and counting bytes and so on. And who's a Unix or Linux user might know the program word count, WC. It's not the toilet around the corner, it's called word count. Anybody used WC so far? Wow, all our experts. Anybody programmed a WC? Okay, good, that's a good sign, because you reuse code, that's good. So let's see, let's say a layman person's version of WC, just counting non-whitespace characters by introducing a counter variable, introducing a variable that I use for reading in characters, and if I look closely enough at the definition of the shift character for reading input from standard in, or from iStream, it will automatically skip white spaces unless the stream is set into a mode where it says don't skip white spaces. But the default mode would be skipping white spaces. Yeah, that's stateful APIs. You see, the stream API is the oldest one of C++, and it's the one with the worst design that you get. It uses inheritance, which can be very threatening. It uses stateful stuff and side effects. And that's the problem is with I/O, you can only have I/O with side effects, and that's why everything got munched into that. And now we have, as long as this reading is successful, which will be unsuccessful once we reach the end of file, we increase the counter. And then in the end, we output the counter and a new line. That's the basic core version of the WC program. Word, actually counting characters. Now that's the version without a loop. Not even calling a real algorithm, it's just a plain function there. The thing is to map the streams to algorithms, something that's called a stream iterator. There's a thing called an iStream iterator and an OStream iterator. So iStream iterators read, O stream iterators write. And we pass in the stream that we want to read from as constructor argument, and we have to specify what type we actually want to read from that stream as a template argument to the iStream iterator. And there's a nice trick. Whenever we work with these algorithms, we always have to specify a range, a begin and an end. But how do we define the end of a stream? And that's a trick. It uses a default constructed iStream iterator object of the correct type, and that one will actually denote the end of the input when it's done. So instead of writing a loop and using auxiliary variables, we just call out distance with the two iterators and output the return type, which will actually, distance will count how often I can increment the iterator until I reach the end. And that's the exact same functionality as above without any own variables or loop conditions.
And this gives white space as well.
Yes, because the iStream iterator actually uses the input shift operator for reading the values that you expect, which is character in that case, but it could be ints, so you could read the number of ints on the input that you could read successfully. Anybody used an iStream iterator so far? Only few. Okay, that's, you see, that comes in my first lecture in C++, or maybe the second one. That's important. Because iterators are the glue between containers and data and algorithms. Okay, next task. The number of bytes. Well, there we could set either the stream to non-skip whitespace, which is actually called std no skip ws. Or we could use another code piece, and that's wrong. That's why it's red. So that's the first attempt, the red part. Okay, I just use get. The problem is get doesn't return 0 when it reaches end of file. It will return end of file, which is -1 in disguise, and that will still be true. So the red code is wrong. It's an endless loop unless you manage to enter a character value of 0 on your input stream to actually break the loop. So red part is wrong. So how can we do it right? Well, I can still use a character variable and use the version of get that actually reads into that character variable, and that version of get will not return the character red, but will return the stream object itself, like the shift operator in our example before. And whenever the stream hits the end of file, it will get into a mode that's no longer good, and then the loop will break out and I can output the count. But again, that loop can be written with just calling out the distance function. And the only difference here is I have to use a different kind of iterator, and that's called the iStream buff iterator. Don't hit me with the name. It's just some legacy. The stream buff is an implementation mechanism of the iStreams, and the iStream buff iterator takes a plain draw input and then will tell you, iterate over the individual characters in the input of the stream. But again, the code is almost identical except for these 3 characters where the iterator type differs, and again the distance will tell us how many characters are in there, and that's a word count for characters without skipping whitespace. And there's a question in the back.
What would happen if in this iterator example we had used the iStream iterator without the buff? What
Then
would
we
be
have
the
the
effect?
example of before where we skip the white space the white space in the input.
So these three, this iterator takes into account the white space.
This iterator will read every character on input regardless of its values.
Okay. Thank you.
And it doesn't use get, but a thing that's equivalent to get. So the code actually is more or less equivalent up there with the get reading the character. But the specification looks a little bit different, but that's only readable by people who know how this is implemented.
What if I wanted to count the number of UTF-8 characters?
Then I have to use a stream. Well, UTF-8 characters have the good example, they are also bytes. Oh, you mean Unicode characters. You can't do it with that. I'm not sure if the Boost library provides a library for reading Unicode characters. Maybe. You can check over lunch break. So that doesn't work with, it doesn't take into account the Unicode or something like that. What you might be able to do is, I'm not sure. You might have a library that uses, if you use the other version, the iStream iterator, that takes into account Unicode. If you read in, for example, Unicode string classes. But I'm not a heavy user of Unicode to actually make sense of it. Okay, that's the example to get the sorry, I had my animation wrong. That's the version to get to use get without the correct with the incorrect version of get, where you don't pass in the character variable. You could use get, but then you have to specify the loop condition as long as it's not EOF, and EOF is defined as the traits type of the iStream, and there's a helper function returning the value EOF that you actually could compare against. Yeah, that's the iStream buff iterator. Sorry, animation wrong. Now, if I want to count the words, again, back to the example reading the characters. Now watch closely. You just replace character by standard string. And now I read sequences of non-whitespace characters to a string variable and count how often I can do that. And again, I can use distance with an eStream iterator using standard string. So I can count how many words are there on the input. So what have we seen? No loops, easy variation of the theme, and using the iterators. Now, if we want to count how often each alphabetical character happens to be an input, that's a little bit more involved. Any idea how to do that? The thing is, we could either use a map, mapping characters to a counter, or we can, because characters are, let's say, small numerical values, we can just use a big enough vector to count the elements. And this is deliberately made not very nice, but consider this is a main function passing in standard C in and standard C out to two functions, collect and print. And these two functions are testable because they use a stream as a reference parameter, and we can call them from a test case with the string stream, for example, either with canned input or collecting the output and comparing what's there. Now, this is not a very nice implementation because it uses a for each algorithm, which is actually, let's say, the algorithm version of the range-based for loop, taking 2 iterators, and we can't use the eStream iterator in a range-based for. So that's why we need to use the algorithm if you want these 2 iterators denoting the range. And then we use, what is C++11, a lambda. What's a lambda? A lambda is a function definition that is inline, and that you write a function that doesn't have a name. Any mathematicians familiar with the lambda calculus? Or functional programming, if you use Python, I don't know, is it Python where is it called a block or what? Huh? It's also lambda in Python? Okay. In Ruby it would be a block, in Smalltalk as well. So you write just a piece of code and pass in that piece of code as a value. That's what a lambda is about. And you have the round parentheses for the function parameters. You have a function body. And to denote it as a lambda, you have angular brackets. And between these brackets, you can provide a so-called capture. That is whatever you take from the surrounding scope and place it to use it within the lambda. And because we want to change the values in this vector, we pass that vector by reference into the lambda. So the lambda code refers to the v outside of the lambda, and we just, at the position of the character, we increment the vector v. And because we started each value with 0, when we defined the v, we actually increment the characters. And why am I using at here? Some of you told me you know how to use vector. What is at doing? What's that? It's like the brackets in the vector, but where's the difference? It checks the bound. Why does this code uses this thing? Because it uses code that might not work well on all compilers. You don't know if char is signed or unsigned. If you compile that on a compiler where char is unsigned, everything works fine because I get the values from 0 to 255. If I use it on a compiler where char is signed, I might end up using negative indices if I have, let's say, non-ASCII characters in my input. And that might just break my vector, and if I would have used the index operator directly, I might get undefined behavior and might have overwritten some memory or whatever. And that's why I use at here to be safe on the safe side. But it's inefficient. Just remember. The trick that I could use have used to make it work is use unsigned char here as a parameter type. Then I would have known that everything that comes in is between the range of 0 and 255, more or less, on most platforms, except for some strange ones where a char is not a byte.
We need some slide up instead of for each here, which is not very nice. Why don't you like for each?
Because many times there are more interesting algorithms that are better telling you what you're doing. With the for each, I always have to look at the function that's called here for each element to see what the loop is doing. I can use for each to almost, let's say, do most of the other algorithms that better spell out what they are doing. For example, I could use accumulate to sum up something. And I might have used accumulate to implement that as well with some tricky thing to do. So it's, I would say, for each is the algorithm of the last resort, because it's not much better than a handwritten loop, because you always have to look into the body actually of the loop to understand what the loop is about, or what the algorithm call is about. With many other algorithms like find or findif or count, the algorithm name tells you what it does without having the need to look at the specific details. You don't see the loop, or you don't have to consider the loop body to understand what it's doing. That's why set for each is kind of cheating algorithm version. Okay, that's yeah. Getting what I want to show you. C++11 has a nice syntax for type aliases called using. Anybody use typedef in his/her life so far? Typedef is ugly because you have a hard time, if it's a complicated type, to actually see what name you're defining. And using makes it easier because you say what name you're defining, and then an equal sign, you spell out what type you're defining it at. You can even have using aliases for templates. And I implemented in the cvelop library actually a refactoring where you can, if you have a typedef, you can replace it by a corresponding using type alias to make it your code looking nicer or more modern. Again, we are using that here for the stream iterator. Here, this is a case where you have to use the round parentheses because we want 256 elements in the vector and not 2 elements with 256 and 0. We have the lambda with the capture, and there's one thing where you have to use a typecast. I could have written char li here, and I choose to opt for the type conversion operator because the return type of std to lower is an int and not a char. If I just used auto, I might not have gotten the character here, but the ASCII value of the character that is spelled out. And if I would have used curly braces for value construction, then it would be a narrowing conversion, and the compiler would not compile that, I believe. It's a compile error. So the curly braces to construct a value will take into account that you don't use narrowing conversion. It would be nice, especially if you, let's say, take a double value and would put it into an int. There, the curly braces would warn you against the cutting off the decimal digits. If you want to change that for words, we can no longer use the trick with a vector, but we can use a map instead, or an unordered map, which would would use hashing. So we map strings to counters where we use an unsigned type, and the loop is looking almost the same. I believe so, yes. Except that we replaced characters with strings, and for the telling, for the map, we get pairs. So we have first for the key and second for the value. And you could ask me why it's not key and value as in all other sane languages. That's the reason where there was too much code reuse in the standard library, where a pair of values is used to represent key values, but a pair is used more often in the standard library in other places. Like sometimes the function returns a pair of iterators. Some functions return a pair of an iterator and a bool. And that's one of the curses. I would have preferred to have key and value here, but that's history not being rewritten.
Excuse me, Peter. Why they have to be strings? Excuse me at the moment. Why cannot be a map from char to size D?
Because I wanted to count occurrences of each word.
Got it.
I could have used map
wa-
in the
I was in the
example
wrong
before,
example.
and now I just use strings. And again, we see the lambda with the reference capture because we want to change the variable outside of the map. It's almost the same code. We have the range-based for loop for... Yeah, sorry.
I was wondering, why didn't you use a const string reference in there?
Where?
So with the lambda.
Just to make it fit into the slide. And again, I expect the words to be quite short. And there's a thing called small string optimization, where actually the string class doesn't need heap memory to represent smaller strings, maybe up to 15 characters or so. And therefore, it's not really very expensive to pass a string by value. So it's, and constref would have made the code too wide, or I would have needed another line. That's why I didn't use const string ref. In C++ 14, I could have used auto constref here. In C++ 11, there's no type deduction for lambda parameters yet. That's why I love C++ 14, because you could write lambdas with auto here, and it makes life much easier as a lambda author. It's just something, when you see it, it's so obvious, and then you see, why didn't they do it in C++ 11? Well, not brave enough. Compiler writers reluctant. But I think lambdas aren't the biggest thing that went into C++ 11. Const expr is a bigger part. That's another version using an unordered map, and as you see, it again is exactly the same code, except that we just replaced this map with unordered map. Unordered map relies on hashing, where map relies on sort capability, or less than comparing. Hashing only works well for built-in types and types defined in the standard library, because defining your own hash function that works well is magic or hard, and the standard library doesn't yet provide facilities to create a good own hash functions combining hashes of other, maybe of members of your classes, if you want to use your own classes as keys in a hash map. That's why I don't recommend using unordered map with your own classes as keys. And it might not perform well in, let's say, situations where you don't read often. So this would not perform better than the other maps if, let's say, the words only occur once. And it's could have worse performance and memory consumption than the map that actually sorts the words. And also, because it's unordered, the output would look much uglier, because the keys would no longer be a nice sorted sequence, but just randomly, or whatever your hash function or hash unordered map implementation does to these strings. So the output would look much uglier and much harder to actually see if it's correct. That's all I said. Okay, what you can hash is actually strings and smart pointers. There, the standard provides hashing infrastructure that should work well enough depending on your library implementation. Okay. I said summing up numbers is an interesting thing. And I think you all write algorithms where you, let's say, reduce something to some number in the end. Do you? And to test things like that, we can again use unit tests. For example, if we expect sum to return 0, if there's nothing to sum up, that's good. That's an assertion we can take. If we sum up a single value in a stream, we expect the output be equal to that single value. And if we sum up multiple values, well, I made up that example exactly, so it should sum up to 42. With, according to the question before, with the inaccuracy of the lowest representable decimal digit. Now to actually test that, we put our sum function in a library. We define the API of taking a stream that we want to read the numbers from and returning a double, so we expect some double numbers on the stream. And again, the implementation is almost trivial, so it's doubtful if we actually have to write a test for that sum function, but it's just to show you how to implement things like that. There's a very universal algorithm called accumulate, which actually does a reduction using the plus operator. You pass in a range and a starting value, and it will, as it says, accumulate, add every element in the range up to that, onto that starting value and return the resulting value as a function result. Accumulate comes in an overload with an additional parameter, which takes actually the reduction function. So you can, instead of the plus operator, you can pass in your own binary function that takes the starting value plus whatever the element type is and does whatever it is. Like if you want to have the inner product, you just pass in multiplies and then you get all the values multiplied. But then you mustn't use 0 as a starting value. That would be a bad idea. Questions? Easy peasy? The main function would just call sum with standard in and put out the numbers, and you, as long as you enter valid double numbers, it will just sum, and in the end, when you either enter something that is not a number or something else, it will just finish the input and output whatever you entered summed. You see, no loops needed. Multiplication table. So those you who have, let's say, children at the age of whatever age you learn that, 8, 9, multiplication. A multiplication table, 1 to, let's say, 20, 1 to 20, and all the multiplications up to 400 in the lower right-hand corner, or for you in that corner, will actually, should be printed. So if you want to, we create a vector where we want to have the 1 to 20 in that vector. And we could start out with 21s and then use the algorithm partial sum, which actually does what it says, a partial sum of the values. So we have, let's see if we can show you what it does. There's enough space. So we start out with 1s. Partial sum copies the first element, 1. Computes the sum of the first 2 elements in the second position. Computes the sum, actually takes these 2, and so on, until we get 20 in the vector. That's what create partial sum, create PS does. And print times 4. Well, we take our vector type, the value type. So instead of, do I need that still? Oh, I should have used here VT because I extracted that here. Then we iterate over the sum, and we use transform, which is actually a copy algorithm that performs a function for every element that it copies from. And as we see, we are looped twice over the vector. Here we take the vector as an outer loop for every element in the vector, so 1 to 20. Then we call transform again for the vector elements, and we use an O-stream iterator, which we haven't seen. This is the opposite version of the I-stream iterator. You use the shift operator to output something to a stream. And this O-stream iterator outputs a value, which happens to be an int, and a comma and a blank after each value. And we take the I from that context, take the element in the vector, and return the multiple of I and the element. So for each element, we iterate over the whole vector and multiply that element with each element in the vector, which is actually giving us the multiplication table in the end.
Why do you write v dot begin twice in this partial sum?
Good question. Partial sum takes an input range, and it needs a range where to put the output of the range. Partial sum takes the start and the end iterator as the input. And now the partial sum will create a result for each value in the input, and it has to store that result somewhere. So it takes an input range plus an output range where to store all the results. And I override the vector itself, which is okay because I first read and then I write the corresponding element into the vector. So I can take the vector itself as the output range of the partial sum overriding a vector. I could have used another vector with enough space, or with the back inserter to actually create that into another vector. That would have been possible, but I just override the vector. So partial sum actually takes two ranges, one for the input and one for the output. And the input range always comes with a begin and an end iterator. And the output range, only the start is sufficient because it knows how many values to output from the input range. Good question.
And it is in the algorithm specification, the algorithm description, where you can find that this is actually okay. In other algorithms, you cannot do it. Okay, you can always do it, but you don't know what the output will be. In this case, you're guaranteed that the output will be okay, right? That's
I hope so.
Yeah.
Otherwise, my code is incorrect. I'm not claiming that my code is always right. It might be unit tested. What's that?
Well,
I guess partial sum will be vectorized if the compiler is good enough.
and it's difficult to vectorize partial sum in general, I think.
Yeah.
So, but I don't know.
In that case, well, this might not be vectorized because we don't get that. But other algorithms will be vectorized, yes. Depending on what kind of input data you provide. But vector is good to vectorize because everything is contiguous in memory. And that's typically recognizable by the compiler.
Can I?
Anything that I wanted to tell you?
Can I ask?
Yeah.
One remark. I would say stud algorithms are very, very good. You need to learn about them, right? And you need to have richer vocabulary, because if you have 4 loops, you can specify everything with like 3 words, and with the algorithms you need more. But once you know that vocabulary, you can do a lot of cool stuff. And another thing I wanted to see what you think, Peter, is the fact that you have a for loop there around the transform, and that is basically because stud algorithms do not compose, which might be fixed in the next release of range-based STL algorithms. So in which you can say for each and transform something.
Actually, you could cheat by using for each and a bigger lambda. Oops, why did that? Does someone has a Bluetooth thing coupled with my, or maybe my mobile is not turned off? Come on. Ah, my mobile connected. And my hip was actually doing the paging. Come on, where? That's a sum. Multiplication table, okay. How did that happen? Okay, you could cheat there and use a for each and call the transform in the in a lambda. But it's not nicely nestable. So let's say the algorithms don't nest nicely. Ranges will change that, and there are libraries out there today that you can use where you can actually do things like transformation and filtering on the fly while iterating and make it more composable. There's even, if you go for CPPCon 2015, there was a talk on transducers, where actually the algorithm combination using the kind of streaming and filtering things can actually be implemented in C++14 or 11 quite nicely to get that easier. But it's not in the standard library yet. And as always, if you want to standardize something, you not only have to have implemented it, you have to have experience with the implementation, and you have to agree on the design, and there's always some corner case where someone is not happy with the design of someone else. And you usually cannot have, let's say, some engineering trade-offs are there, and you have to decide which trade-off to take, and that can be a lot of arguing about which trade-off is better for the world or not. Now, let's look back at what you can do with lambdas to get a little bit more of the syntax. With auto, you can actually store a lambda into a local variable, or even a global one. You have to use the brackets to introduce a lambda. Even if you don't have a capture, you have to use the brackets. If you don't have parameters, you can leave out the parentheses. If you don't have a return type, or it cannot, or it can be easily deduced, you don't have to specify the return type. And you can access global variables, because you can access global variables everywhere. So using cout in a lambda is something I wouldn't recommend, but it's possible. If the lambda has parameters, you have to use parentheses. And if you're lucky enough to be able to use C++14, using auto as a parameter type for type deduction is quite helpful, especially if you want to pass the lambda to an algorithm as an algorithm parameter for modifying the algorithm's behavior. Auto there is a lifesaver, because spelling out the type of the values where your code is applied to might be a little bit tedious. What you can also specify, if the return statement in the lambda is returning an expression of a type that's not quite right, and you want to change that, you can provide a return type, but that's optional. Like, for example, here, this lambda odd taking an int should return a bool. And to compute the odd numbers, I just return the remainder of division by 2, and that is either 0 or 1. 0 is considered false, 1 is considered true, so whenever it's odd, like it says here, we return something that's convertible to true. And ints convert nicely to bool, but if I want to deliberately say, okay, this please return that as a bool, I can say so by using that little arrow and write the type of return type here. The even version, just above, there's return type deduction, and there it's returning a bool because I have the equality with 0 that will return the correct type. In C++ 11, lambdas are restricted to a single statement, which usually is a return statement to make it useful. In C++ 14, you can have arbitrary code in lambdas, and that's much nicer to use. Especially you can have arbitrary complex code in the lambda with other loops and other calls, multiple statements, and multiple return statements. As long as these multiple return statements agree on the type they're returning, the return type deduction for lambdas works well. And that's usually why you see these return arrows quite rarely. Captures. Within a lambda, you can use global variables, and if you want to use a variable from the surrounding context, you can use the variable name as in the capture, then it will capture that variable. You can capture a variable by reference by using an ampersand in front of the variable name, or you can capture everything by copy with equal, everything that you actually use in the lambda, or you can capture everything that you use in the lambda by reference with an ampersand symbol. In C++ 14, you can even introduce new variables as capture variables within the lambda by giving the variable name equal initial value. That will introduce that name in the scope of the lambda. It will keep its value. And if you want to change that variable within the lambda, you have to mark the lambda as mutable. But that syntax is C++ 14 only. Here, for example, because we want to refer to that x, we have to pass it in and declare the x outside or use a constant. Is there a question? Sorry.
Yeah. Could you explain the mutable behavior? So as far as I understood here, I could, for example, implement a counter with this lambda and then execute the lambda each time, and then I would get a count, or?
As we have seen, the lambda with the counter, actually the counter has to be passed in by reference, so the lambda refers to the variable defined outside of the lambda. All other variables, all variables that capture by copy are const within the lambda, unless you specify the lambda as mutable. So with the lambda definition, because it introduced new syntax, the C++ committee did the right thing. Everything is const unless otherwise specified. And the keyword was already there with mutable. That's why we get mutable. I would have liked to have everything const and specify mutable whenever you want to change it after initialization, but that train went out of the station maybe 85 or so, when Bjarne introduced const into the language, and we no longer can change that. But with lambdas, everything is const unless you specify it as a mutable lambda. And I'm sure I have somewhere an explanation, but I don't have it right now in this slide set. lambdas without captures actually are compatible to C function pointers. So for example, if you want to use qsort of the C library, which is available in C++ as well, which I don't recommend that you use that, but if you're really eager to see how lambdas work as function pointers, you can write a lambda that takes the role of the qsort comparator function pointer, and because it doesn't have a capture, it just works because lambdas without a capture are compatible to function pointers with the same signature. And the comparator of qsort takes two void pointers because it's the C-ish version of generic code and returns an int. And if we have an array with ints, we can use qsort to sort it with that nice casting the void pointers to int pointers, dereferencing them, and then subtracting them, and we're getting the specified behavior of the comparator of qsort for ints. Don't do that. Just use the sort algorithm. That's just to showing you how it could be done. The corresponding sort would just take begin A, and everything would be fine. Bit shorter than that qsort call. Mutable. Here we are. If we use a lambda where we capture a variable by value and want to change that variable within the lambda and keep the changes for subsequent calls of the same lambda, we actually have to specify the lambda as mutable. And that's the same as with variables. These are consts unless we specify the lambda as mutable. When we want to specify the lambda as mutable, even if we don't have any parameters, we have to use the parentheses to actually have the place for the keyword mutable. And there's a question in the back.
So this mutable applies to all captured variables. I mean, if I would write, how is it called, a function object, I could mark single members as mutable.
Right.
But if I have a lambda with mutable, everything is mutable. Is that correct?
If I make a lambda mutable, everything is mutable within the lambda. If I want to have more specific control, I have to do my function object myself. Internally, for those who know what a function object is, a lambda is internally represented as a function object by the compiler. And the call operator that is overloaded in that function object is by default a const member function, and if I write the lambda with mutable, it will be a non-const member function, and then that way I can change the member variables that you get from the captures.
Just to clarify, with that int x at the top there is not modified. So it's copied, and then the internal copy is, in a sense, the data member.
The original x stays the same as it is. And that's the C++ 11 version of such a generator generating the squares of numbers. Generate n is an algorithm again that takes a place where to store elements, an output iterator, a number of elements to generate, and then a parameterless function that will generate values for and be called subsequently n times for the generating the values. I here use a back inserter, which is a wrapper around a vector that will use pushback to insert values into the vector, to the end of the vector. And to actually make a generator work, the generating function must have a side effect, otherwise I would get all the values the same. And then I could use another algorithm which is called fill n, which would fill a value into a container or whatever range I provide. And this generate n actually requires a parameterless function, and to have that generate different values, it must have had some state and side effect to modify that state. And there's another question there.
Since the lambda has now its own copy of x, could the int x be const in the beginning?
Sorry, I didn't understand.
Could the int x curly brackets, could it be const because the lambda has its own copy of it?
Yes. So the outer variable x that gets copied into the lambda could have been const here. Another special case to look out for, if you use lambdas in member functions, some call that methods, but in C++ it's called a member function, there you always have this object. And if you take everything by value, you always get this pointer, which is a pointer in C++, by value. And when you refer to a member variable of the surrounding class within the lambda, you implicitly get that member variable by reference. So if we have a class with a member variable x and use within a member function of that class a lambda that refers to that x, it actually changes that x without being mutable, because it gets a copy of this pointer. It will not never be able to change this pointer, but it will be able to change the object referred to by this pointer. That's a thing to remember, that if you use lambdas in member functions, that this object can be changed even though the lambda is not mutable.
And there is a proposal for C++ 17 to fix this behavior.
Let's say, make it a little bit more consistent. What time do we have the lunch break planned? 12 or 12 some? Huh? Now. Good time for a break.